Hello, my dear students. The topic of discussion of this lecture are the topics which we left over on the last lecture, the lecture number 4, where I was planning to cover these three topics: convex combination and convex sets, then convex hull and convex polyhedron, and afterwards the topic of simplex. But I could not do the last two. So, in today's class, we will start our discussion in the topic of convex hull and convex polyhedron. And then we will define the concept of an extreme point, and we notice that we are slowly moving towards proving that extreme points of the feasible set of a standard linear programming problem is just the vertex of the geometric region given by the constraint set. Fine. Towards proving this, we need some concepts on convex sets, and you notice that the idea of convex sets, or in general convex analysis, this topic convex analysis per se a vast topic, and convex analysis per se a topic of research nowadays, where we call analysis of convex functions, convex sets, under the umbrella of the analysis of convex analysis, and broadly convex optimization. But here obviously we are not getting into the topic of convex analysis or convex optimization rather, but we notice that here a linear programming problem is a very special kind of convex optimization problem. And in order to identify that the vertices are precisely the basic feasible solutions, we have to get into some topic of convex analysis, very basic concepts. Those are convex sets, convex combination, convex hull, convex polyhedron, extreme points, simplex, and so on. So let's start our class today in the topic of convex hull. By convex hull, what do we mean? By convex hull, we mean the following. By convex hull of a collection of points, so let's suppose I have a collection of points, or just I have a set, a subset of the n-dimensional Euclidean space. So let us suppose S be a non-empty subset of Rn. Then we call the convex hull of the set S is the convex combination, all possible convex combination of the points inside the set S. The collection of all possible convex combinations of the points in S is called convex hull of the set S, which is denoted by capital H of S. Fine. So that is what the definition of convex hull. Okay. Now let me consider a few examples. For instance, let me suppose I have in the set capital S, I have only these 3 points in the R2 plane. And then what are the collection of all possible convex combinations of the points in the set S? So the set capital S here is the points x1, x2 and x3 say. So 3 points I have taken in the R2 plane, and what are the convex combination, what are the possible convex combinations of all these 3 points? We note that you can choose a pair of points out of these three and you take their convex combination. Convex combination of 2 points is a line segment. Convex combination of x2 x3 is this line segment. Convex combination of x1 x3 is this line segment, right? And now you notice that a particular point here is a convex combination of the point x1 x3. Fine. Now you consider the convex combination of x2 and this point. Fine. And therefore you notice that any point here, here or here, any point in this line segment is a convex combination of x1 x3 and x2. Fine. And therefore you notice that the set of all possible convex combinations of the points x1 x2 x3 is this entire triangle. Fine. So the convex combination of the 3 point set x1 x2 x3 that I have taken here, these 3 point for these 3 point sets, the convex combination is the triangle this x1 x2 x3. Fine. Similarly, if I take 4 points, then it will be a quadrilateral. If I take just a pair of points, it will be a line segment. If I consider 5 points, then it will be a pentagon, and so on. Fine. For instance, now I take an example of not just finitely many points, but I consider set of all points inside this circle. Fine. Then what? So I consider the set of all points on the boundary, on the periphery of this circle. Fine. So I'm not considering the disk here. I'm just considering the periphery of the circle, or that we call as circle. So for if I consider the set as the points on the periphery of this circle, then what is the convex combination of that set? For this set is the convex combination is the set of all points inside this closed disk. That means set of all points inside as well as on the boundary of this set. Fine. So convex hull is this entire circular region. Fine. So that's all about the idea of convex hull. And we notice that here is a special case of convex hull. When you have a finitely many points in the set capital S, then you notice that the convex hull of finitely many points in the n-dimensional Euclidean space will give us convex hull as a polygonal region. Fine. And this polygonal region in the n dimension is called a polytope or polyhedron. Fine. So by a polyhedron we mean the following, that if x is finite, if the set S is finite, if it is a finite subset of the n dimensional Euclidean space, is a finite set of Rn, then finite and non-empty we have to consider. Sometimes we call, if it is having no element, then we call it as it is having zero element. Zero is also finite. So by finite we mean it is just a non-zero number here, or let me precisely say the set is a finite but non-empty. Finite non-empty subset of the n-dimensional Euclidean space. Then the convex hull of S, then the convex hull of S is called a convex polyhedron. Fine. And therefore convex polyhedron is obviously convex hull of just finitely many points. And if you have a very special kind of polyhedron in the n-dimensional Euclidean space that is having n precisely n plus 1 number of vertices, that polyhedron is called, that set is called a simplex. Fine. So here a polyhedron in Rn having precisely n plus 1 number of vertices, having a precisely n plus 1 vertices is called a simplex in Rn. Fine. So in R2, what are the simplexes? In R2, we notice that example in, let me start with R1. That means in the real number line, what is a simplex? In the real number line, it is one dimensional, that you all know, and therefore any polygonal region will reduce to just a line segment. So line segment, as it is having precisely n plus 1, that is 2 vertices, therefore we call that line segment a simplex in R1. In R1, a line segment is a simplex, or any simplex is a line segment. In R2, what are simplex? In R2, simplex is a triangle, because triangles are precisely regions with precisely polyhedron, and that polyhedron is having n plus 1, that is 2 plus 1, 3 vertices. And here many times I have said vertices. What do you mean by vertices or vertex? Let me define what we mean by vertex. Vertex of a convex set is defined as follows. Vertex of a convex set is a point which cannot be expressed as a convex combination of any other 2 points. So if I consider a convex set, let's suppose capital S, so the point, let's suppose a point X in S is said to be a vertex of the convex set capital S if there does not exist any pair of points. If a pair of points x1, x2, and which are distinct, x1, x2 belonging to S and x1 not equals to x2, such that the point X, let me call it not a generic X, but let me consider a specific point X bar, such that X bar is lambda times x1 plus 1 minus lambda times x2 for some lambda strictly inside 0 to 1. Fine. So such a point X bar is called a vertex of the convex set S. So here, for instance, if I am considering a triangle, say, and for this triangle, what are vertices for this triangle? Precisely, you notice that this point is a vertex, this point is also a vertex, this point is also a vertex, because for this particular point, if you are taking out, then for this point you don't have any other pair of points x1, x2 which are distinct, such that x bar is equal to lambda x1 plus 1 minus lambda x2. That means such that x bar is contained strictly inside the line segment joining x1 x2. By strictly inside I mean you have to exclude the end points, because you are not considering here lambda as 0, you are also not considering lambda as 1. Fine. So this x1 x2 are obviously then has to be different than x bar. X1 x2 are distinct, and x bar has to lie in the line segment, strictly inside the line segment joining the points x1 and x2. Fine. And now try to find for this particular point in the set S, can you be able to identify, here set is this triangular region. Now here corresponding to this particular point, can you be able to identify a pair of points such that the line segment joining those two points is consisting this point? There is none, right? However, if you take this point in this edge, then you notice that you have this point and this point in the set S such that the line segment joining them is consisting this cross point. Fine. You consider a point over here, let's suppose strictly inside the triangular region. Then you notice the following. You have a point here in the vertex, then you also consider a point over here, this cross point, then you join the line segment. You notice that this point is inside this line segment, and therefore we notice that specifically none of the points on the edge except these extreme points, except this point and this point, except these kink points, is a vertex. Fine. And none of the points in this region, inside, strictly inside the triangular region, is a vertex. Fine. And therefore specifically for this triangular region, the vertices are precisely the kinks here. Similarly, if you take the quadrilateral region, for a quadrilateral region, you notice that the vertices are again precisely the kinks. Fine. And similarly for pentagonal or any other region. Now, for instance, if I consider the points on this disk, fine, can you be able to identify the points which are vertices for this disk? For this disk, the vertices are precisely the boundary points here. The points on the periphery of this circle, those are vertices. Because for any point in the periphery, you don't have any pair of points which consist, the line segment joining those two points is consisting this dot point. And therefore, this dot point is a vertex. However, any point inside this circular region is not a vertex. Fine. So this is what your idea about vertex. Now, what does the idea of simplex says? The idea of simplex says that a polyhedron having exactly n plus 1 number of vertices, a polygonal region in the n-dimensional Euclidean space having exactly n plus 1 number of vertices, fine, that is called a simplex. So a simplex in R1 is a line segment, in R2 it is a triangle, in R3 a polyhedron region having precisely 4 vertices. Precisely 4 vertices will produce you a tetrahedron. Simplex is a tetrahedron, right? Now let me tell you a very special thing in this course, that is the method simplex. You notice that we are slowly approaching to develop a method to solve a given linear programming problem, and the method, most ancient method, and from where the topic, the name operations research has been coined, is the simplex method. And why the name of that method is simplex, that will be clear later on, and we'll find that the name of the method is simplex due to the fact that the you are moving from one vertex to the another vertex in the simplex method, and from one vertex to another vertex I mean one vertex to another vertex of the feasible region corresponding to the feasible region corresponding to the given inequality or the constraint set ax greater than equal to b, x greater than equals to 0. We notice that uh, this set of all points x such that x equals to b and x greater than equals to 0, this set is called a feasible set, and this is also called constraint set of the problem. Constraint set of the LPP, which is stated as maximization of C transpose X subject to this. Fine. This set of points which are satisfying x equals to b, x greater than equals to 0. This set of points, as you all know, collectively they produce a geometrical region, and that geometrical region is a polygonal region that we all have seen in the last day. Now here you notice that if it is a polygonal region, I am just considering one figure in the R2 space, a polygonal region you consider, and you notice that any polygonal region can be observed as union of triangles, and thus triangles are thought of fundamental region to construct a polygonal region. Fine. To construct a polygonal region, I mean you need a finitely many triangles to take union of finite to observe a polygonal region. It is just a finitely many triangular region, right? And therefore, triangles are the fundamental region in constructing polygonal region, and thus, hopefully, where nowhere in any book it is mentioned why the method's name is simplex, but possibly due to the fact that triangles are fundamental regions to construct polygonal region, and polygonal region are the feasible set of a given linear programming problem. Thus the method that we are going to describe is named as simplex, because in the method that we will describe, the simplex method, we will find that from one table to the another table we are jumping from one vertex to the another vertex of a triangular region, and thus the method's name is called simplex or simplex method. Fine. It is not that the method is very simple and that's why it is called a simplex method. Simplex is due to the fact that to construct a polygonal region, the fundamental region is triangle in R2 space. In R3 space, if you want to find a polyhedron region, then a fundamental region is a tetrahedron. Fine. So what do you mean by this fundamental region? By fundamental region, I mean a region whose finitely many union, so finitely many fundamental region should construct a polygonal or polyhedron region. So such regions are called fundamental. For instance, you notice that this polygonal region can also be observed as union of several straight lines, but you will require in that case infinitely many straight lines. So straight lines are not fundamental region. Fine. Anyway, so this is all about your simplex. The definition simplex is precisely a polyhedron region having precisely n plus 1 number of vertices. Fine. Now let me get into a few necessary analytic results from which we will be able to prove that basic feasible solutions of the feasible set of a standard linear programming problem are precisely the vertices of the geometric region given by the constraint set. Fine. You consider the geometric region corresponding to the constraint set or corresponding to the feasible set, and then you filter out what are the vertices. You will find that the vertices are precisely the basic feasible solutions. That is what we are going to prove. And to prove this, now let me start our result with a very fundamental fact that the set of all feasible solutions of an LPP is a convex set. That we all have seen on the last day, but let me just state it, that this result. Now, this is a standing assumption from now onwards, although I have stated many times that this is a standing assumption uh, from the lecture, starting from the very beginning, that any linear programming problem that I will be referring, when I will speak the word linear programming problem, by that I will mean the following, that this is my last announcement about an LPP, that as and when I will be referring an LPP, unless otherwise specified, by LPP I will mean the following LPP, that it is a maximization of a linear function, maximization of C transpose X subject to AX is equal to B, together with you have X greater than equal to 0. Standard form of LPP. So once I am speaking LPP, by that we will always refer the standard form of LPP. So if I am just speaking LPP, by that I will mean this problem only where C is a vector, a constant vector in the n-dimensional Euclidean space. X is generic variable, X is in Rn. The matrix A is of order m by n, so that you have precisely here m many equalities, and B is a vector, constant vector in Rm, and all the components of B's are non-negative. Fine. So these are all your assumptions in a standard linear programming problem. And as and when I will be referring LPP, by that I will mean just only this LPP. And together with this, I have the assumption that rank of A is equal to M. Fine. So there is no redundant constraint here. None of the row can be replaced by a linear combination of other two rows. Fine. And thus the rank of the matrix A we are considering is equal to M. By that we also sometimes say rank of A is the full row rank or full rank. By full rank I mean the number of rows here, which is M, and here M is less than equals to N, and therefore the matrix capital A is having full rank, means it is having the maximum value of the rank, and maximum value of the rank, that you all know, is less than equals to minimum of M and N, and therefore M. So the maximum possible rank of the matrix capital A in this setup, that M is less than equal to N, in this setup the rank is maximum possible M, and we are assuming that the rank is equal to M. So by that we mean the matrix A is of full rank. Fine. Well, now for this LPP we are going to slowly prove that basic feasible solution are precisely vertices of the geometric region of the constraint set. Fine. So let me now start with stating the following result. The first result is that the set of all feasible solutions by feasible solutions I mean any point which satisfies both the restrictions of the feasible set. That means the set of all feasible solutions, by that I mean this set, that is x belonging to Rn, such that x is satisfying x equals to b together with x greater than equal to 0. Fine. This set is a convex set. So we can talk about vertices of this feasible set. Fine. And the proof of it is very simple. Last day we have already shown how to prove it, and let me now skip the proof and I directly go to the next result. The next result says that if there is an optimum solution of this LPP, then that optimum solution must be assumed by one of the vertex or one of the extreme point of this feasible region. So I neatly state that if there is a finite optimum value, that means the feasible set is not an unbounded region, and even if it is unbounded region, but the solution of the problem, by solution of the problem I mean the minimum value of the objective function, maximum value of this objective function c transpose x is finite. Fine. So if there is finite optimum value, if there is finite optimum value of the LPP, by the LPP I mean I refer this LPP that I stated earlier, finite optimum value of the LPP, then the objective function of then the objective function of the LPP, then the objective function C transpose X assumes its optimum value at an extreme point of the feasible set. Fine. Now here we will, as we will prove later, that the extreme points and basic feasible solutions are equivalent, and you all know that the basic feasible solutions are finitely many. At maximum you have the number of basic feasible solution is NCM, that we all have learned, and therefore number of extreme points of the feasible set of this LPP is obviously finite. So let's start assuming that the extreme points of the feasible set suppose the extreme points of the feasible set are this x1, x2, xk are extreme points of the feasible set. The feasible set is convex, and therefore we can talk about extreme points. And why only finitely many points are there in the extreme? Finitely many extreme points are there for the feasible set, because you know there are finitely many basic feasible solutions, and later on we will prove that basic feasible solutions are extreme points. And therefore, as basic feasible solutions are precisely at max NCM, therefore the number of extreme points are finite. So we are assuming here x1, x2, xk are extreme points of the feasible region. By feasible region or feasible set we mean the same. Fine. By feasible region we mean the geometric region given by the constraint set or the feasible set. Fine. And now as in the result we have assumed that there is finite optimum value of the LPP. there is finite optimum value of the LPP means this function, objective function C transpose X, gets maximum value at a very specific point in this feasible set, because you have to find the maximum value of this objective function in this feasible set. Fine. For instance, this is not the scenario for every linear programming problem. For instance, let me suppose I wanted to maximize the function x1 plus x2, and I have the constraint set as follows. My constraint set I am just simply taking up, and the constraint set as this region. This is obviously a convex set, and it is also having only two vertices, this point and this point, finally many vertices. But here you note that if I am trying to maximize this x1 plus x2 in this region where this line, let's suppose, is this x1 plus 2x2 is equal to 1, say, and in this region you notice that this objective function does not get any maximum value in this feasible region. The objective function x1 plus x2 does not get any maximum value in this feasible region. Fine. So when this objective function, or in general the objective function C transpose X, gets a maximum value, I am saying, by that I am meaning obviously that there is a point in the feasible set at which this function C transpose X gets its maximum value. Fine. And you have assumed here there is a finite optimum value of the LPP. So there exists a point. So by assumption, as there is a finite optimum value of the LPP, there exists a feasible point. By feasible point, I mean a point in the feasible set. Feasible point or feasible solution, they are different names for the same concept. That a point that satisfies both the restrictions x equals to b and x greater than equals to 0 is called a feasible point or a feasible solution. So there exists a feasible point xm such that the maximum value of the LPP C transpose X is equal to C transpose XM. The maximum value of C transpose X, by that I mean the maximum value in the feasible set. So maximum value on the feasible set, that X equals to B together with X greater than equals to 0, you have C transpose XM. And XM is satisfying both this restriction X equals to B and X greater than equal to 0. Fine. Now what we have to prove that this point xm is either an extreme point, or there exists at least one extreme point at which the value of the function C transpose X is identical to C transpose xm, and that will prove that the optimum value, which is C transpose xm, is given by an extreme point of the feasible set. Fine. So we have to prove either xm is an extreme point, or we have to prove that there exists some extreme point xp, say, for which C transpose XP is equal to C transpose XM. And that's all you need to prove. And to prove this, therefore, so to prove this, if X, so here you have two possibilities. XM is either an extreme point, not an extreme point. So we break into two parts now. If XM is an extreme point, then you are done. That is what you wanted to prove, that there exists an extreme point at which the function gets the maximum value. And if xm is not an extreme point of the feasible set, then we have to proceed with some analytic steps. So let me start the first assumption, that if xm is an extreme point, of the feasible set, then the proof is over. there is nothing to prove. However, if xm is not an extreme point, then in that case, we proceed with the following logic. If xm is not an extreme point of the feasible set, then you notice that as x1, x2, xk, these are extreme points of the feasible set, and you know feasible set is a polygonal region, fine, or a polyhedron, and therefore what will happen? The polyhedron is eventually the convex combination of this x1, x2, xk. So any point which is a feasible point, any point that satisfies x equals to b and x greater than equal to 0 is nothing but convex combination of x1, x2, xk, because you know this region x equals to b together with x greater than equals to 0 geometrically gives us a polygonal region or a polyhedron in the n-dimensional Euclidean space. And the extreme points are, you have assumed the extreme points of these sets are this exhaustive collection x1, x2, xk, fine, and therefore we notice that this polygonal region is convex combination of the vertices. So any point that is a feasible solution, obviously convex combination of these vertices, fine, and therefore if xm is not an extreme point, then notice that then we consider then we consider the following. If it is not an extreme point, then we consider this that xm, we consider this equation which is valid for xm because xm is a feasible solution, and therefore xm can be observed as a convex combination of the extreme points. That xm can be expressed by convex combination of the extreme points. So how many extreme points you have? x1, x2 till xk. So lambda 1 x1 plus lambda 2 x2 plus lambda till way up to lambda k xk. So we can, in a compact way summational form, we can just write it as lambda I xi. I is ranging from 1 to k. Fine. And for some lambda I is, all lambda is greater than 0, and you have the summation of them lambda I is equal to 1. That is what the convex combination is that we have defined on the last day. Fine. So xm is just this convex combination of the extreme points x1, x2 till xk. Then we define the following. You now notice the following. Let Zp is equal to C transpose xp, which is equal to the maximum value of the objective function at the vertices. So I take maximum of C transpose x1, C transpose x2 till C transpose xk. Fine. So you consider to find the objective function value as at this vertex, at this vertex, at this vertex, and this all these vertices. You consider and to find and then you find the objective function's value at the vertices, and you take the maximum value of all the objective function value. As these are finitely many, k many real numbers, therefore they will have a maximum, and we denote this maximum as C transpose xp, and that C transpose xp is equal to z. Fine. Now, if this is so, then you notice the following. You have Zm, which is equal to C transpose Xm. We are denoting it Zm as C transpose Xm. C transpose Xm is the maximum most value that we have. This C transpose Xm we are considering. Now Xm is a convex combination, this convex combination. And therefore from this convex combination, one say, we notice that this C transpose Xm is equal to this summation I equals to 1 to k C transpose of lambda xi. So lambda I into C transpose xi. Fine, I can do it because C is just a constant, so I can bring the C transpose inside of the summation. And C transpose xi's are all less than or equals to C transpose xp, because C transpose xp is the maximum most value out of C transpose x1, C transpose x2 and C transpose xk. And therefore each of these C transpose xi is less than equal to C transpose xp, right? So I'm replacing this C transpose xi by C transpose xp inside the summation, and as you have this lambda I a non-negative quantity, therefore this inequality will be intact, less than equal to C transpose xi is less than equal to C transpose xp, therefore lambda I times C transpose xi is less than equal to lambda I times C transpose xp, because lambda I is non-negative. Then you take the summation on both the sides, I equal to 1 to k, and this is equals to your C transpose xp, which is not dependent on this variable I on the summation. So it is C transpose xp I equals to 1 to k of lambda I, which is equal to 1, therefore C transpose xp it is. And therefore you notice that this Zm value, which you have assumed the maximum most value, is less than equals to C transpose xp. And when can it be possible? It will be possible only for Zm equals to C transpose xp, because Zm cannot be less than, strictly less than C transpose xp, because Zm is the maximum most value. It cannot be lesser than the function's value at any other point in the feasible set. Therefore Zm must be precisely equal to C transpose xp, and xp is an extreme point. It's not that. Xp is out of the extreme points x1, x2, xk, and therefore and hence Zm is assumed by, that is what I wanted to prove, that the objective function value assumes its optimum value at an extreme point. Zm value is assumed by the point xp. By Zm assumed by xp, I mean Zm is equals to C transpose xp. The objective function value at Zm by the function C transpose x at the point xp. Fine, and that is what you wanted to prove, which is a vertex. Xp is a vertex. And now next we shall prove the following, that a basic feasible solution of an LPP corresponds to an extreme point of the convex set of the feasible solution. Let me see how much time do I have. Well, I have spent here 48 minutes. Let me then go with, or let me stop here. I will proceed with the proof in the next day, because this proof is a little lengthy. So on the next day I will start my lecture on the topic, on the result, that a basic feasible solution is an extreme point, and then immediately I will prove that an extreme point is a basic feasible solution. Fine, and afterwards we will end up with a particular result, that if the objective function of an LPP assumes its optimum value at more than one extreme points, then every convex combination of the extreme points also gives the optimum value of the objective function. If let's suppose I have two extreme points at which the linear programming problem LPP assumes its optimum value, then any point in the line segment joining these two points, these two vertices, at which the objective function C transpose x gets its maximum value, then this cross point or any point inside this line segment is also an optimum solution of the problem. So if there exist two different solutions of an LPP, there are infinitely many solutions, right? We'll end up with that, and then later on we'll slowly move towards the methodical development of the simplex method to solve a linear programming problem. Fine. So with this, let me end up here. On the next day, we'll prove that basic feasible solution is an extreme point and vice versa. Thank you. Thank you all for all of your kind attention.